We're going to study in this video hydration reactions of alkynes. So hydration here. What hydration means then is we're adding water, but this is across a triple bond in the case of alkynes. So in here we have a couple of conditions. When we did alkenes previously, we studied hydration of alkenes using sulfuric acid, so diluted, and we added water across the double bond in Markovnikov fashion. Same is going to happen with alkynes. The only difference when we study hydration of alkynes is that the product doesn't stay the way it is initially. So we're going to form first an intermediate that is called an enol. So under that condition, hydration happens, what we need to remember is that it will happen in Markovnikov fashion, similar to what we studied before in alkenes. So what it is then that you will add the H at the least substituted, and you will add the OH on that side, adding water across the double bond. So what is our product? Initially, so now you're going to have a double bond. So H here and OH here. This is an enol, but it doesn't stay that way. So that's the main difference with when you are doing hydration of alkenes and alkynes, because this compound, this intermediate, will immediately tautomerize, and you will form the equilibrium. You shift it to that side, you're going to have a ketone when you have hydration under those conditions. This is happening, say, Markovnikov. Again, you remember that you added the H here and the OH. The intermediate is an enol. The tautomerization can happen both under acidic condition and under basic condition. Since we are working here with sulfuric acid, obviously that's acidic condition. So how the tautomerization takes place? So if you have here, say, hydronium here, and that's positive charge. Now, the pi electrons in the enol is going to go acting as a base. And when you do that, you will form the following. I'm not working with that reaction yet. So, adding your H, you're going to get this. And let's throw the O on that side. So you have an intermediate that is a carbon-cation, and then you can do this. You're going to have now water acting as base. Remember that when you are under acidic condition, so here what you have is hydronium and water. So in the first step was a proton transfer from the enol using the hydronium as your base, but here water will be acting as base in another capacity, getting that product, and here you will form your ketone. That's a product. So that's your intermediate, the enol. But it's probably easy if you remember that the region selectivity, this is similar to Markovnikov, so H here, OH here, you form this enol, and that is your intermediate. And notice that when you form these enol here, the OH is like in the middle, it's not terminal. That is the main difference when we use the other reagent. This is similar to borane. We use borane when we had alkenes. So when we had, say, an alkene, and we wanted to do the anti-Markovnikov hydration, we used borane was BH3. So we did hydroboration oxidation. That is, we did that with alkenes. So just that. And now, in the case of alkynes, we don't want to use borane because, as we know, alkenes will react with borane. So it will go again and add across the double bond. So we want to use a bulky, actually, a derivative of that. We're going to be replacing two of the H's by something really big and bulky. So we use a couple of those reagents, and one is we call 9BBN. That is a bicyclic structure, really large. And we also use diacetyl borane. So meaning it is two isoamyl groups on the sides. Two R groups, large. So we'll add only one hydrate to the double bond. So I'm going to erase that part of the mechanism because now I am interested in showing what happens in the other reaction. Now we are under different conditions. What we did before with hydration and acidic condition, right? And that was my tautomerization step. And let's just remember that this is what we had in the medium. And when we explain that. So using these bulky boranes that can only transfer one hydrate, what we need to remember is that borane will add anti-Markovnikov, is the Regent selectivity. What that means, similar to alkynes, is that we are going to add now the H at the more substituted and the OH's terminal. So we're going to make a different intermediate. This time is this. And so what I did is I added the H here and the OH on the other side. So what that is anti-Markovnikov, similar to that. Anti-Markovnikov Regent selectivity. And again, we're not using borane because we don't want to add again. So, but this is not the product. It happens similar to that. We don't isolate the enol. And these intermediates are called enol because notice that they have a double bond, so in and all for alcohols. So these are enols. Now, under this time, the reaction is hydroboration, oxidation under basic conditions. So it's different. The tautomerization step is now catalyzed by base. So I'm going to write the product and then I'm going to show how it's formed. Since the OH is at the end, now we're going to make an aldehyde. So notice the big difference. If you use these conditions, which will form the, say, Markovnikov enol, you get a ketone. And if you use the hydration, oxidation, you will form an aldehyde, because then you had added the OH at the end. Because you are under basic conditions, the tautomerization happens in a different fashion. What you have is OH and water. And that is important to remember. What do we have in the medium? So if we have OH as base, the first reaction that is going to happen in the tautomerization step is actually acid-base. So for the sake of the space, I'm going to draw this. And now, throwing that here. And here you can do now this, and you can have water as your acid. And so, in doing so, you will be forming a terminal carbonyl or an aldehyde. So it is, the mechanism is different because in the case of the basic condition, well, base is OH, your acid is water. And in the case of the acidic condition, you have hydronium and the base will be water. But bottom line, what we need to remember is that we can do hydration two ways with Markovnikov Regent selectivity forming an enol that will tautomerize to give you a ketone, since you have added the OH here at the more substituted carbon. And if you use a different, say, a bulky borane, let's say, substituted, we will get a terminal enol that will tautomerize to give you an aldehyde. So things to remember that. Under this condition, with sulfuric acid, you get a ketone because you form that enol. And with 9-BBA, for example, you are going to get an aldehyde.